If R be the relation on the Cartesian product of n with itself, here n represents the set of natural number defined by a comma b related to c comma d if and only if ad times b plus c equals to bc times a plus d for all ordered pair a comma b and c comma d belonging to the Cartesian product of n with itself. We need to check if R is an equivalence relation or not. Okay, let us begin. So here we have the ordered pair A comma B related to the ordered pair C comma D, and it's related by the equation. So that means if and only if we have AD multiplied to B plus C equals to BC multiplied to A plus D. So this is given to us. Okay, so here we have the ordered pair A comma B related to C comma D, and it is related by this particular equation. That means if this equation is true, then it will be true that A comma B is related to C comma D and vice versa. Okay, now using this we need to show whether if R is an equivalence relation or not. So to show that a given relation is an equivalence relation, we have to show that it is reflexive, it is symmetric, and it is transitive as well. So first we begin by checking out whether if it is reflexive or not. That means we are going to check for its reflexivity. Now, what is reflexivity? Reflexivity simply states that if we have, let's say we have a relation R, so R is going to be reflexive. R is going to be reflexive if and only if we have an ordered pair A comma A belonging to the relation R for all A belonging to the set A, meaning the relation R is defined on the set A. This is how we can define, this is how we can check whether if a relation R is reflexive or not. For this, what we will do, we are going to consider an ordered pair A comma B. Actually, we need an element, so here our element here itself is the ordered pair A comma B. So let's say this ordered pair belongs to the Cartesian product of the natural number with itself. Okay, now this would mean, that means if we take the ordered pair A comma B and we relate it to the same ordered pair A comma B, then according to the relation, this is our definition of the relation. What should we get? So here we will be getting A multiplied to, now here we'll take the help of this equation, and whenever we see C, the letter C, we're going to replace it with the letter A, and wherever we have the letter D in lowercase, we're going to replace it with B. Okay, so let's do that. So A remains the same. So D is going to get replaced with B. So we have A times B multiplied to B plus C. But C is going to get replaced with A. So this must be equals to B multiplied to C. So C is going to get replaced with A. So we have B times A multiplied to A plus B. Fine. Now, is this equation true? Yes, that's a true equation because AB is going to be equals to B. They're commutative. And B plus A equals A plus B. So here, the left hand side, AB times B plus A, that's exactly the same as BA times A plus B on the right hand side. Now, what does it tell us? This tells us that, thus, we can say that it is true that A comma B is related to A comma B for all ordered pair A comma B belonging to the Cartesian product of n with itself. Okay, so we can say that our relation R, this is reflexive in nature. This is a reflexive relation on n, the Cartesian product of n with itself. Okay, so reflexivity is done. So let's now go to the next type. That means we need to show that the relation R is also symmetric. Now, to check for symmetry, what we'll do, we're going to consider two ordered pairs. So let's say we have the ordered pair A comma B, and then we have another ordered pair C comma D. Let's say these two ordered pairs belongs to the Cartesian product of n with itself, such that the relation A comma B related to the ordered pair C comma D simply means that we already have this definition. We have AD multiplied to B plus C. So this is going to be equals to BC multiplied to A plus D. However, what we can do, we can rewrite it as, we can take the left hand side to the right hand side and the right hand side to the left hand side. So this is going to become BC multiplied to A plus D. This is going to be equals to AD multiplied to B plus C. So here what we can do, we can again rearrange because we know multiplication is commutative. So in place of BC, here we can rewrite it as CB multiplied to D plus A. This is going to be equals to DA multiplied to C plus B, because addition is also commutative. Now the reason why we're written in this fashion, this is nothing but we are saying here that C comma D, the ordered pair, is related to A comma B. Now to help you understand what we can do, this is our main definition. So this is how the relation R is defined. Now we have A comma B related to C comma D, and here we have showed that C comma D is also related to A comma B. All we have to do is we take the help of this particular equation. So here we're going to replace A with C, and wherever we have C, we're going to replace it with A, and then we're going to replace B with D, and wherever we have D, we're going to replace it with B, and we'll see that this expression, so if we in this particular expression, so if we replace A with C, B with D, and this C and D with A and B respectively, then we are going to get exactly this particular expression. Now the whole reason of doing this is we started out by considering that A comma B is related to the ordered pair C comma D, and we were able to show that C comma D is also related to A comma B. Now what does this tell us? This simply tells us that R is symmetric. So R is a symmetric relation on, it's a symmetric relation, R is a symmetric relation on the Cartesian product of n with itself. Right? So we have successfully showed that a given relation R is also symmetric, and now we'll go to the final one. We'll have to show that it is transitive as well. Now to show that the given relation R is transitive, what we'll do, we will suppose that let the ordered pair A comma B, then we have another ordered pair C comma D, and we have one more ordered pair E comma F. Let's say these three ordered pairs belong to the Cartesian product of n with itself. Now we'll have to show that if we have the ordered pair A comma B related to the ordered pair C comma D, and we have the ordered pair C comma D related to the ordered pair E comma F, then it must be true that the ordered pair A comma B must be related to the ordered pair E comma F as well. So this is going to be our goal. That's what we need to show. Okay, so let us begin. So here we have A comma B related to the ordered pair C comma D, and we have the ordered pair C comma D related to the ordered pair E comma F. Fine. Now A comma B related to C comma D, what does it mean? A comma B related to C comma D, this simply implies, we'll take the help of this definition, we have A multiplied to D, we have A times D multiplied to B plus C. This is going to be equals to B multiplied to C times A plus D, and we have C comma D related to E comma F. So this simply means that we have C multiplied to F, that means C times F. This is going to get multiplied to D plus E. This is going to be simply equals to D multiplied to E multiplied to the sum of C and F. So we have C plus F. Okay, fine. So here we have two equations. Now what we'll do, we're going to divide both sides of this equation with A, B, C, D. So that means we have B plus C divided by BC. This is going to be equals to A plus D divided by we have AD. Fine. Now furthermore we have 1 over B added to 1 over C. This is going to be equals to 1 over A added to 1 over D. Fine. And then from here what we'll do, we're going to divide both sides with CFDE. So that gives us D plus E divided by DE. This is going to be equals to C plus F divided by C times F. And when we simplify it, we're going to get 1 over D added to 1 over E. This is going to be equals to 1 over C added to 1 over F. So here we have two equations. Both of them are equally valid. What we'll do, from this equation, let's isolate 1 over C. So 1 over C, that's going to be equals to 1 over A added to 1 over D minus 1 over B. So here we're going to take this 1 over C and we're going to substitute in this particular place. So our equation is now going to become 1 over D added to 1 over E equals to 1 over C added to. So in place of 1 over C, so let's use 1 over A added to 1 over D minus 1 over B added to 1 over F. So here we can immediately cancel out 1 over D from both sides. We'll transport this negative 1 over B to the left hand side, and that's going to give us 1 over B added to 1 over E. And then on the right hand side we have 1 over A added to 1 over F. Fine. So let's further simplify. So we now have B plus E divided by BE. This is going to be equals to A plus F divided by AF. Cross multiplying, we get AF multiplied to B plus E. This is going to be equals to BE multiplied to A plus F. And if we compare it with our definition of the relation, this particular definition, this is simply telling us that we have the ordered pair A comma B, so that is related to the ordered pair E comma F. We can verify that. So here we have A times F, that's exactly what we're getting, multiplied to B plus E. This is going to be equals to, we have B times E multiplied to A plus F. Fine. So here we have been successfully able to show that A comma B, this ordered pair, is related to the ordered pair E comma F. Fine. So that means this simply means that the relation R is transitive as well. So this is transitive as well, and hence we can say that our given relation R is an equivalence relation. This is an equivalence relation, and it's going to be an equivalence relation on the Cartesian product of the set of natural number with itself.